All right, today's goal. The learner will understand exponential and logistic functions, exponential functions and their graphs, the natural base E, logistics function in their graph, population models, and why exponential and logistic functions model many growth patterns, including the growth of human and animal populations. Okay, so let's go over a couple definitions to remind us of exponential growth and exponential decay and logistic functions here, okay? All right, so exponential functions. Let a and b be real number constants. An exponential function in x is a function that can be written in the form of f of x equals a times b to the x, where a is a non-zero, b is positive, and b cannot equal 1. So key things there, b has to be positive and b cannot equal 1, and a is not 0. The constant a is the initial value of f, the value at x equals 0, and b is the base, okay? Exponential growth and decay. For any exponential function f of x equals a times b to the x, any real number x, f of x plus 1 equals the base times the function. If a is greater than 0 and b is greater than 1, the function f is increasing and is exponential growth. So when a is greater than 0 and b is greater than 1, it's a growth function. The base b is its growth factor. So if we look at this, two times 3 to the x. The initial value is 2, and the growth factor is 3. Okay? Because both 2 is greater than 0 and 3 is greater than 1. Okay? Now, if a is greater than 0 and b is less than 1, the function f is decreasing and is exponential decay function. The base b is the decay factor. So, now remember, both a and b have to be positive. So when it says b is less than 1, that means it's between 0 and 1. Okay? So if I say this, then the initial value is 3, and the decay factor is 1/4. Okay? So let's look at a couple examples. It says determine formulas for the exponential functions g and h whose values are given in the table below. Okay, so let's look at g first. Now remember, the initial value, so we need to come up with this. G of x equals a times b to the x, or look at it this way, a times b to the x. That's a dot, not a... Okay, so the initial value, though, is when x is 0. So what did it equal when x was 0? It equaled 4. So I know a is 4. And then the growth factor is, what is it growing by every time? Well, what is it growing by every time? 3, 3, 3, 3, because you can do the reverse. What's 36 divided by 12? 3. 12 divided by 4? 3. And I know b is 3. So you have g of x equals 4 times 3 to the x. Let's look at the next one. So h of x is 0. Go across. So I know a is 8. 2 divided by 8, 1/4. That's how they're getting this 1/4 as well. So b is 1/4. So I have h of x equals 8 times 1/4 to the x. So there's our equations. Let's look at some more examples, guys. Okay, it says describe how to transform the graph f of x equals 2 to the x into the graph of g of x equals 2 to the x minus 2. Okay, so remember, we've seen this. Standard form. a times b to the x minus h plus k. And there's also, I should have a c up here. Okay, and remember h is left or right, k is up or down, a is vertical stretch, vertical shrink, and c is horizontal stretch and shrink. So we've seen these before. So if it looks like h is 2, so that means it's shifted 2 units to the right. So let's take a look at the picture, the graph of it real quick. So here it is. Now, if you look at the initial value of f of x, f of 0 equals 2 to the 0, which is 1. So I would plot that point 0, comma 1. If I do that on the graph here, 2 units to the right. If I move to the right 2, see how that's where it moved to? So we got that right. Okay? So let's look at the next example. It says, describe how to transform the graph from f of x equals 2 to the x into the graph g of x equals 2 to the negative x. Okay. Now, remember, if a was negative, that would mean a reflection over the x-axis. When the exponent's negative, or it's attached inside the parentheses here, that means it's a reflection, or when c is negative, that means it's a reflection over the y-axis. So you would say reflected over the y-axis. So picture this, picture this one flipping over the y-axis here. Only it was never shifted right too. So let's take a look and see what that picture would look like. So see how the initial point here stayed the same, but it, instead of going up, it's coming down. So it looks, since it was reflected, that's like a decay factor. Okay? And if you think about that, doesn't the negative exponent mean to take the reciprocal of the base? So that would be like 1/2 to the x. Okay? Alright, let's look at some more examples. Okay, the natural base e. E is equal to the limit as x goes to infinity of 1 plus 1 divided by x to the x power. Okay, that's just a fact that we need to remember. Alright. Any exponential function f of x equals a times b to the x can be rewritten as a function as f of x equals a times e to the kx for any appropriately chosen real number constant k. So if a is greater than 0 and k is greater than 0, f of x equals a times e to the kx is exponential growth. If a is greater than 0 and k is less than 0, f of x equals a times e to the kx is exponential decay function. So let's look at another example. This says, describe how to transform of the graph f of x equals e to the x into the graph of g of x equals e to the 3x. Okay, so 3. So that means, remember now, these ones are always the opposite of what you think, because you want to say it's a horizontal stretch, but it's a horizontal shrink by a factor of 3. Okay, let's take a look at that picture, meaning it's going to go up faster, because if you horizontally shrink, it's going to go up quicker. Okay. So see how it's going up very fast? Because if you think about this, if we did f of x, f of 1, you get e to the first. If you do g of 1, you get e to the 3 times 1, which would be e to the third. See how when x is 1, you get e to the first, but when x is 1 here, you get e to the third. It means it's getting up quicker. Okay? Alright, so there's an example of growth. If it was negative 3x, that would be the example of decay. So let's look at another definition. Let A, B, C, and K be positive constants with B less than 1, but positive. A logistic growth function in X is a function that can be written in the form of f of x equals c divided by 1 plus a times b to the x, or f of x equals c divided by 1 plus a times e to the negative kx, where c is the limit to the growth. So, meaning c is the largest value you're going to get when this is 1. Okay? So, we'll be doing some examples in class with that bracket, but I will see you guys tomorrow.